Welcome back, everybody. This is our video solution to problem 5 from quiz 5, spring 2023, Math 302, Cal State Fullerton. And we are back to looking at functions and relations. So we got a bunch of example ones here. So we want to give examples of the following or explain why they cannot exist. All right, let's look at the first one. A relation from the non-negative real numbers to the real numbers that is not a function. So in order to establish that we have a relation, we just need to have, right, to be a relation here, we need to have a subset of the Cartesian product of the non-negative reals with the reals. That's it. That's very easy to do. So the important, interesting part here is that we want it to be not a function. And so what does it mean if we're going to say we have a relation that's not a function? Well, to be a function, you have to have the property that every element of the domain, remember the domain here is the leftmost term of the Cartesian product, every element of the domain has a unique image. Okay, an image means there's a corresponding element in the right-hand side, right? So if we're looking for an element here, right, what is this as a set? These are all pairs, x comma y, where x is a non-negative real number and y is a real number. Okay, so in this pair, x is some element of the domain and y is its image. And so if we are going to have a function, we would need to have for every possible x a unique image. There has to be exactly one y such that xy is in the set. Okay, if we want it to be not a function, then we need to find some x which has no image. All right, so there's a lot of ways to do that. So here's one. What if I define a relation, let's call it R. Okay, so it's just going to be a subset of this Cartesian product. And it's simply going to have all things of the form x comma x, where x is a positive number. So if I did this, then of course I'm looking at things, right, in the non-negatives, because heck, x has to be positive. And then the image is a real number, it's just x. Now, why is this not a function? Well, I need for every non-negative integer, I need to have an image. But here, I only have images for positive real numbers. I'm missing 0. Okay, so this would be an example. What if we draw a picture? Here's another example. What if I draw something like that? Okay. Now, this would be not a function for a couple of different reasons. First, say this is at 1. Everything to the right of 1, right, all of those real inputs, I have no outputs. So again, not a function. But also even between 0 and 1, for each of these inputs, I have 2 different outputs. So this would be not a function. So there's infinitely many ways, right, you could think to do this. Lots of creativity allowed here. But the important part is that you need to either find some element of the domain that does not have an image, or at least one element of the domain that has more than one image. All right, so let's move on to part B, which is asking us for an injective function with domain R and codomain Z. So this is actually a very tricky one, and it's going to turn out that it's not possible. The general idea here is that if you have an injective function, you're going to be putting, you could think about putting your domain into the codomain. Like you have a copy of the domain inside the codomain, which would mean you have a copy of the reals inside the integers, or at least something the size of the reals inside the integers. But the real numbers, right, in a cardinality sense, are larger than the integers. So this isn't actually going to be possible. So the argument we could write down is that this is impossible since the image of R via an injection, right? So an injective function. So you're not going to take any elements of R and send them to the same place, so the image is going to retain the same cardinality. So the image of R via an injective function is uncountable, because the real numbers are uncountable. But the image of R is a subset of Z, right? So since the image is uncountable and a subset of the countable set Z, okay, and you cannot have an uncountable subset of a countable set. All right, so we'll move on to C. In C, we have a surjective function, or at least we're looking for one, whose domain is 1, 2, 3, 4, 5. And, oh my goodness, that's like the kind of thing an idiot would have as the combination on his luggage. Huh. Okay, so codomain A, B, C, D, E, F. All right, so can we build a surjective function? So if it's going to be a function, okay, so again, we're looking for a function, then that means that every element in the domain, 1, 2, 3, 4, 5, has to have a unique image. Okay, now it could be that 1 and 2 have the same image. That's not a problem, but for sure, 1 can only go to one thing, right? It has to have one image. 2 can only have one image. There are 5 elements in this set, so at most, they have 5 images. But this codomain has 6 elements, and for a function to be surjective, every element of the codomain must have a preimage. But there are only 5 elements in the domain to be preimages. So this is going to be impossible. All right, so since the codomain A, B, C, D, E, F has cardinality 6, a surjective function to this set, 1, 2, 3, 4, 5, 6, must have 6 distinct preimages. And the domain has only 5 elements. Okay. Okay, thus no surjective function is possible. Okay, so how about the final one, D? We want a bijection from the integers to the integers. Oh, well, let's just stop right there. Bijection from the integers to the integers. Well, how about I just use the identity function? Send every element to itself. That's a bijection, right? Everything, it's a function, right? Everything has only one image, itself. It's surjective. The preimage of something is itself. It's injective. There's only one preimage, right? Oh, but wait, there is more. Let's see. Such that no odd integer has an odd preimage. Ah, nuts, right? I wanted to send 3 to 3, but now that doesn't work because 3 would have itself as its preimage. And that's an odd number now with an odd preimage. All right, so we have to think harder. Well, what if I just swap things around a little bit, right? So maybe we'll draw a little picture to indicate what's happening. So for example, I have 0, -1, -2, etc., 1, 2, 3, etc. And what I could do, I'm going to draw another copy of these integers, dot, 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 -1, -2, -3, whatever, dot, dot, dot. What if I just swapped things? So like 1 and 2 and 2 and 1. So 1 goes to 2 and 2 goes to 1. And then I could have down here, like I have a 3 and a 4, 3 and a 4, and I send 3 to 4, and I send 4 to 3. And I do that everywhere except for 0, perhaps. All right, so -1 will go to -2, -2 goes to -1. And 0 I can just send to 0. All right, now in this case, if I have an odd integer, I want to know whether it has an odd preimage. So I'm looking at this odd integer is coming from the codomain. How do I know? Because I'm looking for a pre-image. Okay, so where does, for instance, 1 come from? The pre-image of 1 is 2. Pre-image of 3 is 4. Pre-image of 5 would be 6. Pre-image of -1 is -2, and so forth. Okay, is this going to be a bijection? Well, everything in here, yeah, you can see there's going to be an arrow going into everything, and there's only one arrow going into everything. Okay, now can we write this out explicitly? Okay, well, let's see. So I want to have a function f from z to z, and there's maybe a special thing going on with this 0, so maybe we'll write that explicitly. F of 0 is equal to 0. But now, what if I have an odd integer? Well, I want to send it to basically one more than itself. So if I have, and at least for the positives, all right? So if n is positive and odd, then I'm going to send f of n to n plus 1. And if it's even, f of n will go to n minus 1, right? 2 goes down to 1. And what if n is negative? If n is negative and odd, let's see, -1 goes to -2. There I'm subtracting 1. So f of n will be n minus 1. And if it's even, I'll send it to n plus 1. Okay, so here's a little challenge for you. See if you can simplify this presentation of the function, right? Can you simplify in the sense of, oh, maybe have it so I don't have to break it up into essentially 5 different cases, right? Put that in the comments if you can do it. All right, now we would like to maybe verify that this is going to be a bijection. I mean, we have a good sense that it is. All right, so how do I know that f is, say, surjective? Well, I need to show that everything has a preimage. So we already know that 0 has preimage 0. So that's covered. What if I have n greater than 0 and say n is odd? Okay, so like a 3. Where does that come from? Well, that actually comes from 4. Okay, so 3 came from 4, which is 1 more than 3, right? So then n has preimage n plus 1. Okay, what if n is even? If n is even, it's like a 4, then that came from 1 less, right? So it has, n has preimage n minus 1. Okay, and I'm going to leave the n less than 0 case as an exercise for the reader. Okay, how about injectivity? So f injective. Well, to show injectivity, we usually will take 2 elements of the integers and show that they had to come from different places, right? So, or that they go to different places, rather. So let's let x and y be integers. All right, let's make a little room. So such that, well, let's assume that f of x is equal to f of y. We want to show they're actually the same, right? That's enough to show injectivity. Okay. Well, if x and y are integers, then they're 0, or they're positive, or they're negative. If they would be odd, they could be even, right? So there's lots of little things to check here. All right. Well, we'll be systematic about it. So I guess maybe this f of x and f of y equals 0. Okay. So if f of x equals f of y equals 0, well, we know that 0 has only one preimage, right? Namely 0. Why? Well, if I took say a positive number, then if it was odd, we were going to add 1, and that makes it still positive. If it's even, then it's no smaller than 2, and that means when you subtract 1, it's no smaller than 1. And for a similar argument, right, when n is negative, you're not going to be able to get down to 0. Okay, so then x and y are both equal to 0. All right, because 0 has only one preimage. Since 0 has only one preimage. Okay, so what if they were both positive? So if f of x and f of y, of course they're equal, are positive. Well, now it's either odd or even. Okay, then if f of x is even, of course that means f of y is even. Okay, or maybe we'll start with odd, right? Follow this. If it's odd, then that means that f of x is actually equal to, well, we know x plus 1. So f of x is equal to x plus 1. But also f of y, we know that's equal to y plus 1. And f of x is equal to f of y. So x plus 1 is equal to y plus 1. And that implies that x is equal to y. Okay? And let's do the other case. If f of x is even, well, in that case, f of x is going to equal x minus 1, and f of y is equal y minus 1, but f of x and f of y are still equal, and so that implies that x minus 1 equals y minus 1, and so x, again, is equal to y. Okay, so similarly, if f of x equals f of y are negative, we conclude x equals y. Okay, and so that's enough here, right? We're able to conclude this function is both injective and surjective. All right, now there's another reasonable way that you could have shown that this f was a bijection without having to go through the surjective and injective bits, which is to show that f has an inverse function. So what would be the inverse, right? So here I'd want to have I can actually just call it f inverse, right? From z to z. But now this is originally this was the codomain z, and now it's turning into the domain, and this was the domain z, which is turned into the codomain. And what is this function going to do? All right, well, this function also will send 0 to 0, and you would say, oh, okay, well, now what if n is positive and say it was odd? Then I'm just going to follow exactly the same thing, right? I'm going to send f of n to n plus 1. It's actually the exact same thing, because what's going to end up happening, right? Let's say I start with 3. I send it to 4, and now here we'll do the even bit here. So f of n equals n minus 1. So if I start with 3, this f sends it to 4, and now this f inverse says, oh, it takes 4, sends it back to 3, subtracts 1. Okay, so these two functions are going to undo each other because every odd instance is going to turn it into an even, and then the even just sends it back. Okay, so we do a similar thing with n less than 0, right? It's essentially the same function, isn't it, right? You notice this? So it's actually f. This is kind of a neat thing. So in this case, when you're odd, f of n will be n minus 1, and f of n is equal to n plus 1. And you see this is all exactly the same stuff. This means that f inverse actually equals f. So this function has the property that when you apply it twice, it becomes the identity function. So this is a special type of function. So the technical word here, when a function is equal to its own inverse, is called an involution. So f is an involution. In the language of group theory, which we'll get to later in this course, we'd say this has order 2. Order 2 elements are also called involutions. All right, well, that's the end of quiz 5. We will see you next week with quiz 6.